Welcome to today's webinar. Today we will show you how you can design timber shear walls in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Gerhard Rehm will be the presenter today. He is responsible for the development of the timber design add-ons, and he works also in the customer support team. Then I say something how you can ask questions during the webinar, at least for the attendees who participate the first time. First, I switch off my webcam that you can see the full screen. If you have a question, just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Gerhard. Gerhard, you can start.
Andreas, thank you very much and welcome from my side to today's webinar about shear wall design in RFEM 6. So let's start with the content for today's webinar. So the first small point will be the theory. I was thinking about how deep I should go into this theory stuff, and I decided, to not go in detail so much. It would cost me a lot of time. There is such a brilliant literature already in the internet, or you can buy some books. So I'm sorry, I cannot directly recommend an English literature. I'm used to the German one, so but I'm sure there will be definitely brilliant literature about this issue or about this topic, and then it should be fine. Okay, then we will directly model some timber shear walls, or exactly we model one wall and go through all the steps, and I will explain you in detail every step and exactly how we model the timber shear wall. Of course, we will design it afterwards, and as you can see here on the right hand side, we will also focus on openings, which is an important topic, of course. And at the end, we will have an outlook to the next features, what we are working on. Okay, so the first step is just a quick overview about what is a timber shear wall. I guess most people are familiar with it. We talk about some plates, top plates, bottom plates. We talk about studs, depends on if they are on the edge or on the inside the shear wall. We have openings, door or window openings. And especially on the sheathing. Here we talk about the sheathing joints, which are essential for the design. So we cannot consider this as one sheathing. We of course consider multiple sheathings. Fasteners, that's of course an important topic as well. So I guess also in other countries in Europe, the staples are getting more common compared to the USA or Canada. They still use nails mostly, but I guess in industries, the staples are more common, but we offer both at the moment. Okay, then of course, because of the horizontal force or lateral loads, we will get some, and the wall height, we will get some forces which causes some tension or compression as well, of course, but we focus on tension very often in timber shear walls. Here we have, different kind of hold downs or so-called hold downs. Here an innovation from Saxon company which is quite easy for installation of the walls, or the classic anchoring with some hold downs and some anchor bolts. If you're interested in this innovation, just go for this company name and you will find further information. And the last slide in this theoretical part is about this shear panels, or about this ideal shear panel. So this is the basic of the Eurocode design. Of course, when we apply some lateral loads here, because of the equilibrium, we need to fulfill also here on the bottom side the same force. Of course, we need to bring down this lateral force to our foundation. And this works via this shear flow. So we need to transfer our horizontal force from the beam to the sheathing, and then from the sheathing back to our bottom plate in this case. And here inside this ideal shear panel, of course the shear flow is always the same. And we get here our tension forces and here our compression forces. Here we need to place some hold down or a hold down, and here in this compression area, of course, we need to make sure that the bottom plate will be able to handle the compression perpendicular to the grain. Okay, then here just a few equations from the hand calculation, and maybe it's already familiar to you, and if not, I will go through this equation quickly. So of course, what do we need to fulfill? We need to fulfill that our shear flow, our ratio from shear flow to our capacity needs to be smaller than 1.0. And the capacity is split into three so-called failure modes. Failure mode 1 is about a fastener. Of course, we need to make sure that our fastener can bear the load. Failure mode 2 is the shear strength of the sheathing. So it's clear the shear flow is also inside the sheathing, and of course this force needs to be covered. And of course we are focusing on the shear buckling, especially when the stud spacing is huge and sheathing is thin. Here we focus on these three equations. So the source of these equations comes from the old German code. It's from the DIN 1052. So especially the second and the third equation. It's also mentioned in the German annex and in the Austrian annex, as far as I remember. There is some simplification in the Eurocode because of shear buckling. We will come to this later and check it directly in the software. Okay, but we have implemented these equations also to all other annexes, and also in the CR code, in this code from Switzerland, these equations are used, and also in the Italian code in the NTC. Okay, I guess, that's it so far. And then we can switch over to our RFEM software and start directly with the first example. Here we will start with a model name. So, I don't know, example 1. And then we come to the type of model. And you must know that we do not use any effective stiffness calculation to design our shear walls or diaphragms. We use an FEA approach, which allows us to consider also the shear flow perpendicular to the grain or perpendicular to the stud direction. And we also consider eccentricities. So we connect our sheathing to our studs by some eccentricities, and therefore we are forced to use the 3D type for model. Okay, and the next thing is the add-on. Here it's an important thing to design or to model the shear walls. We need to use a special thickness type called beam panel, and for this thickness type we need to activate this multi-layer surfaces add-on, same like for CLT. Okay, we don't need some load wizard, but of course we need the timber design. So if you want to design timber frame walls, you need to use the multi-layer add-on and also the timber design add-on. Okay, so here, I don't care. You can use the standard whatever you want. I go with the German one since I'm used to it, but of course you can also use your wished annex. So the timber design for shear walls is available for the Eurocode, of course, for the NTC, and for the SIA from Switzerland. And in near future, so in a few weeks, we will release the design for the NDS code, which includes this SpeedWiz document about shear walls. Okay, and that's it for now. So maybe we can deactivate the member and member set representatives. I don't need them for now or for today. Okay, and in the beginning, we will start with a new material. I go for the studs with a C24 according to EN338. And of course, for the sheathing, we need some panel materials. Of course, we can use some OSB sheathing or some gypsum sheathing for this example, and especially to show you the stuff about backlaying, I prefer to use a gypsum material now. So you can simply enter here gypsum in the search and you will directly get a few gypsum materials, or you can go here to material type and there should be gypsum as well. And let's go with this Gips Rigidur 12.5 millimeters. And what is important here is, of course, for our surface, so the sheathing is modeled as a shell element. We need to consider some orthotropic material model. So we have our basic orthotropic material model available, of course. That was also available in RFEM 5, but in RFEM 6 we have extended this material model to orthotropic timber, which has the big advantage we can distinguish between wall stress and plate stress. And as you can see, gypsum and as well OSB has different stiffness in for wall and for plate stress. So when you would use this orthotropic, this standard orthotropic material model, as you can see, there is only one modulus, and this counts for for plate stress and also for wall stress. So better to use here our timber specific material model. Okay, that's it. Of course, we need a cross section. We can start here by creating a new cross section, 60 by 200 millimeter, for example. And we need to create a thickness. So in this case, we use a 12.5 millimeter gypsum fiberboard. Okay, and that's it for now. So we will switch to our XC plane and we will model our timber frame wall. And I will show you now how to do it. What we do is we create a new rectangular surface, and here we create a new thickness. And when you click here on the thickness type, you are able to select different types. Maybe you know already the layers. And here on the bottom, you will find this beam panel thickness type. When you select this thickness type, then we have the possibility to define the chords and the plates. When you are using only one section, it's enough to leave it as it is. Or when you want to use different sections, then you can switch over here to this tab, and then you can select one section for the top plate, one for the bottom plate, one for the -x directed chord, and one for the +x directed chord, or stud. Okay, we don't need this for now, but I just want to show you that it's possible. Then we need to create the inner studs. So we create here a new inner stud element. We use the same section, makes sense. And here we define the thickness, the distance of the studs. So in this case, the distance should be by 625 millimeters. And it starts, so the orientation starts directly from, or in +x direction. If you want to consider it in -x direction, you can reverse it here. Okay, you can define some offset of the first inner stud, but for this example, we don't need it. Sheathing, as you can see, it's directly set to different. If we would deactivate it and define a sheathing, it would be applied on both sides, which is maybe common for interior walls, but not for outer walls. Okay, so what we do is we define the sheathing on plus or minus axis, plus or minus C axis of the surface. So here in this example, I go with the minus C axis, and I will create this new sheathing. Okay, as a sheathing, we use this 12.5 millimeter gypsum board, and the orientation of the grains. Maybe for gypsum we don't have grains, or in the OSB we have strands. And but in terms of RFEM terminology, I use grain now. Okay, and the rotation is already defined by 90 degrees, so it goes upwards or downwards in this case, always parallel to the y-axis. If you want to change it, feel free to define the angle here. And it's about sheathing in the next step. For now, I'll leave case 1. I will go through this in detail after. But let's start with case 1. And the last option is how we model the sheathing. If we consider the sheathing to the center of the members, or do we want to consider the sheathing to the edge of the surface, edge of the members? So for this example, I want to see the end of the sheathing exactly on the location where the member center is, or the shear center. Okay, so that's it. We go back to main, and here we can define the beam to beam connectors. So how we do define actually the connection from the stud to the top and bottom plate. The default setting is a classical hinge. So as you can see here, it's nothing else than a truss member. But of course, you can switch over to user defined, where you can consider all possible settings from your member hinge. So it depends on which degrees of freedom you wanted to transfer. Of course, we can use some nonlinearities. So if you don't want to transfer any tension, but maybe only compression, that's also possible. Or in terms of compression perpendicular to the grain, if you want to consider some deformation because of the deformation of the bottom plate, when the stud gives compression forces into this bottom plate, you can also use some diagram or partial activity. So it all is possible. But for now, the hinged one is fine. The next important thing is the sheathing to beam connector. So I'll create a new connector. And here we have different connector types, as I said, the nails and the staple. We have different standards available. So the NTC is not available here because it does not describe it, but we can use the Eurocode stiffness calculation in this case as well. When we select Eurocode, we use the current generation of the Eurocode, and here we have actually this issue that the current Eurocode does not distinguish between the slip modulus along the grain and perpendicular to the grain. The NDS and the SIA code, they does, so they use 50%, so they use for the perpendicular slip modulus 50% of the longitudinal shear modulus. In the new Eurocode generation, this is overtaken according to the NDS or SIA standard. So if you want to consider it for now already, you can, for example, create a user-defined one and then simple create a new line hinge and define the stiffness here. But for now, we go with the current Eurocode solution, and I select staple, Eurocode 5, and the diameter, it should be a staple 1.5 millimeter diameter, and the length should be 63 millimeters, and the connector spacing is to be applied by 75 millimeters in my example. Okay. Here we can select if we want to consider the connector stiffness in longitudinal direction only. So this is our classical shear panel where we consider only the shear flow parallel to the top and bottom plate or the shorts. So in this example, I will activate this option, but of course later on we will deactivate this option and then we will see about the differences. Okay. That's it so far. We can continue. And I will draw this wall. It should be 5 meter long and 3 meter high. And what we see now is this simple surface. We don't see any stud right now. We don't see any sheathing. This is simple, this beam panel surface. But here in the data navigator, we already see, okay, there is already members, and there is already one single surface with this fiberboard material. Okay. So the question now is, what is done in the background? As I said, it's an FEA approach what we use, and how does it look like? And this is possible by clicking here on this icon. Maybe you are familiar with this icon already. It's from our surface model member type, and we have the same for the beam panel member type. So I will activate this, and then we will see directly what is done. So you see here we have our studs, we have our top and bottom plate, and that's it actually. But how does it look like in detail? So I will activate this wireframe mode, and then we will see directly, okay, here we have our boundary lines from this beam panel surface, and these boundary lines are connected via some rigid links. So this is a new element in RFEM 6. I guess the most of you are familiar with it already. We use this element to connect our beams to this line. So that means if you apply a support on this line or a load on this line, this load is forwarded to the member in this case, or also the support is forwarded actually to this member. Here you see the member, Here we have the stud with 6 centimeter, and half of the stud is also extended, Or the top plate actually is extended to this edge. Because, for example, when we create a copy of this beam panel, here on top, bottom, you will see that this members are still connected, and that was the aim, of course. And also here from the bottom to the top beam panel surface, we have connected it with these rigid links. So there is a connection. If we would apply some line hinge here on this beam panel surface on the bottom, we would get overtaken this line hinge directly into this rigid link. Okay, I will go undo. We don't need the surfaces for now. Then let's go into 3D and check it in detail what's going on here. So what we see here, we have again this rigid links, and we have the connection from the beam, from the studs or top and bottom plate to the sheathing. So we have two surfaces here. Surface 1 is the classical beam panel surface, and surface 2 is our gypsum surface. And in between there is this rigid link, and as you can see here, this rigid link has assigned this stiffness. So as you can see, we have only a stiffness in longitudinal direction because we have activated this setting here in the beam panel, sheeting to beam connectors. We have activated this option. When I deactivate this option and check the line hinge again, types for lines, line hinge, you will see that the stiffness in C direction is also considered, and then of course we will get some shear flow also in perpendicular direction. Okay, but not for now. We start with this example. Okay, and this is actually the way how we model this this timber shear walls. Maybe one word to these connectors. So when we go to nail and NDS, here in the NDS, they have a more, or they have a better approach actually about this slip curve, since they use already nonlinear slip curves in its standard. So we don't have any nonlinear slip curves available in Eurocode. But of course, if you are familiar with it, or you have some research or some documents, literature, of course, we could implement this here as well. But for now, it's not possible. If you want to do it, if you want to consider nonlinear slip curves, simple, create here user-defined calculation, define the diameters and spacing and so on, and then create a new line hinge. And here you can define your slip curves as you like. Okay, good. Then that's all about this submodel. I think so. Okay, good. Then what we need to do is we need to apply some load, and of course we need to make some supports. So I start here with a support. I use a really simple one, just a classical line support here on the bottom. And since we are in 3D, of course, we need to restrain the Y direction on top. Okay, so for now we are fine with this linear support. We will come to hold downs and so on later. And the next step is the loading. Of course, we need to apply some load. So here I start with the X direction, and I will apply 5 kilonewton per meter on this member here. Okay. Then let's go to our load case. So for this example, I'm not interested in any load combinatorics. So I will deactivate load combinatorics. We will simply use this single load case also for the design. So we consider it as wind, and in Germany we can consider load duration short-term instantaneous, which results in a K-mod of 1.0 for softwood. Okay, I'm not interested in SLS design checks. I'm focusing on ULS, and of course we check the deformation directly in the RFEM add-on, model. Okay, and load combinations. I will create a new load combination, and I simply assign 1.0 the wind. That's it. Okay. Then let's run the analysis. Or maybe before we run the analysis, let's run the structural analysis without timber design and check about deformation and about forces. Okay, so I forgot about to set the FE mesh size. So the default FE mesh size was 0.5 by 0.5. Let's switch this to 0.1 to have at least a few FE elements between the studs. Maybe it's too fine, but for this single surface, it's not a big deal. Okay, so what do we see right now? We see the deformation of the shear wall. We see a maximum deformation of 2.3 millimeter. So maybe we remember this value, 2.3 millimeter. And what we see is also because of the semi-rigid connection from the stud to the sheathing, there will be some gaps as expected. So this is actually the expected behavior so far. But what I want to check is now is the shear flow. So that means the force which is transferred from the member to the sheathing. And of course, this force needs to be designed. So our fasteners needs to be designed according to this force. And we can display this force inside the releases. As you remember, there are line hinges defined. And for line hinges and also for line releases, we can display the forces. And these forces are listed here under releases. So I activate releases and go to line hinges. And here we can go to local deformations, or in this case, I'm interested in the shear flow N, which is along the member. Okay, so what do we see? We see actually the shear flow in each connector. And so it's not ideal. We see the shear flow. We applied 5 kilonewton per meter. At the beginning, the shear flow is a bit less than 5 kilonewton per meter. And at the center, it's a bit higher than 5 kilonewton per meter. So when we remember this graphic here, about the ideal shear panel, we can also go here to result sections. Maybe we should add here the information for releases and go to smooth distribution. So that means we smooth the result, in this case to a constant mean value. And here we can see we get nearly this 5 kilonewton per meter. So now the question can come, why is it not exactly 5 kilonewton per meter? And the reason is really simple. Since the surface is connected here at this location, but the member is 3 centimeters longer on each side, and the load is applied to the member, we have, of course, more load than to transfer via a shorter distance. So what we can do, and I will do it just to prove it and just to make any trust in this calculation, I will go here to varying, and I will start at 0.03 meter with the 5 kilonewton per meter, and it should end at 4.97 kilonewton per meter. So we reduce 2 times the 3 centimeter. Okay. And then let's run it again. And then hopefully we will get this 5 kilonewton per meter, which looks nice. So now we get exactly 5 kilonewton per meter at the, maybe we can remove the FE mesh. Here we go. For the top and the bottom plate. But you see here on the edge, it's less, of course, because the vertical studs are, covering some load as well. And the question now is if this is correct, and of course it is, not correct in terms of timber shear walls, because we have used a single surface now for this shear wall. Sometimes we see RFEM 5 files, which uses some line releases to simulate a timber shear wall, and there we see really often that it's modeled with one single surface, and of course this is not representing a good, correct shear wall, because a shear wall has always some exists always of multiple sheathings. So what we can do now to prove this is to add here a distance higher than wall, the wall length, in this case 6 meters, to force to have no inner studs. And when I run the analysis for this example, which is of course just theoretical, we should get exactly 5 kilonewton per meter. Okay, maybe what is going on? There's some issue now. Yeah, strange. I don't know what's going on. It worked fine. Or maybe, so sorry. Yeah, of course. Sorry, my mistake. I was checking load combination 1. Of course, this is defined as P delta second order analysis, and of course it will buckle out of plane under this high load. Let's check linear analysis. So load case 1 is defined with linear analysis, and load combination is with second order P delta effects. Okay, let's check load case 1. I'm sorry, I was confused. Okay, so now we should get exactly this 5 kilonewton per meter, which is available here, but not exactly here. Okay, I don't know why is it not exactly 5 kilonewton here for this example. I wouldn't need to check it further, but I just want to clarify that, compared to this image, this is the idle shear panel, and this is, just the presentation that we can confirm it. Good. Let's go back. Okay. And we will, check again the deformation. It was 2.3 millimeter. And of course, this strange shear flow, which is not correct in terms of intermediate studs. And the whole problem comes from the sheathing. Because here in the very beginning, I decided to go with case 1. And here we have different cases, and now we will go through these cases. So case 1, is only considering one gypsum surface along the whole beam panel. This is of course not correct. We cannot fabricate some OSB sheathing with 5 by 3 meters, or maybe we could, but of course this makes no sense. It's hard to handle, of course, on the construction side or also in the prefabrication. Okay, then let's check what is case 2. Case 2, this is our classical case. We have sheathing joints directly on the studs, on the vertical studs. This is the most common case, I guess, for the walls. We define here the sheathing unit width. It's 1.25 meters. We also could define some offset here in the beginning. Okay. Let's go through all cases. Case 3 is exactly the opposite. It's horizontal. In this case, it's more for floors where we have one sheathing over the whole beam panel width. We have 3 edges here. At the moment we cannot define any blockings. Of course, this is our an aim. We want to deal also with blockings. At the moment, we cannot deal with blockings. We have always free edges here, but in the future, we will be able to work with blockings. Okay, case 4 is vertical joint and also an horizontal joint. Case 5 is the same, but in the opposite direction. And case 6 is this orientation, which, maybe it's not ideal, especially not for walls. Okay, but let's go with case 2. And now we click OK, and we run the analysis. We remember the how much was it? 2.3 millimeter deformation. And as you can see now, maybe let's switch off the shear flow. And you will see the deformation is 4.1 millimeters, so nearly twice as much as with a single surface. And of course, this is extremely important. And when we check the deformation, so I will increase the deformation factor. So you can maybe switch off here the model. You can perfectly see that the deformation of the sheathing is overlapping. And of course, someone now can argument there is contact from the OSB to the other OSB sheathing. But imagine if there would be compression, there can also be tension. So in this case, we would need to have add some nonlinear condition in between. And of course, this is time consuming in the analysis. And of course, it's time consuming during modeling because of the performance. We would need to create many line releases between these surfaces, which can cause also issues in the performance while modeling. And especially when we think about practical usage, we need to make sure that there is compression, or there can be compression transferred. But what about if you apply the sheathing to the walls? It must be perfectly fitted together. There should be no gap in between, which cannot be guaranteed. And that's why we use this approach. There is overlapping in the deformation, but the influence, I've checked it in an FEA submodel, the influence is nearly zero. It's not worth to talk about. Of course, we can talk about friction in X direction, so along the beam then, because of the sheathing, but come on. We don't do any research for the third decimal place. This is still okay. Okay, let's activate the model again. So we have 4.1 kilonewton per meter, and when we check for 4.1 millimeter deformation, and when we check the shear flow again, maybe deactivate the deformation and go to this rendering. You will see perfectly the shear flow now. It's a bit less at the edges, and at the center it's a bit higher than the 5 kilonewton per meter, since we do not consider an ideal shear panel here anymore. And this is actually the correct result, but it's close to the 5 kilonewton per meter. Okay, so what we can do now is we can design these forces. Maybe let's go first to the timber design, and especially here, let's go to the ULS config. And here in the ULS config, we get a new tab called Beam Panels Connectors. And here we have a few possibilities, a few settings. The first one is about how we want to consider the forces. Should they be considered without any distribution, so just the standard distribution, or maybe some linear distribution or some constant distribution. So the same what we see here. Here, when we use actual, we see it's 4.91 here, and here 4.83. The mean value here gives us some smaller value, a bit smaller than 4.91, which is clear. And also the linear one. And these settings, what you can set here graphically, can be also considered in the design by using this setting. Okay, there are a few more settings which I don't want to mention now, but it's referred here to the Eurocode. You can check what exactly it means. Here on the bottom, it's also clear. I guess you don't have these settings for other annexes, maybe the Austrian one, I'm not sure. But here, these settings maybe important. Here we can reduce the sheathing thickness by 2 mm because of nail heads and staples. You can imagine, not every nail or staple is exactly in the same plane at the end as the sheathing. Dependent on the pressures on the machines. The nail maybe is sunk by 1 or 2 millimeters, and this can be checked here. It's also described in some annexes. In the Swiss standard, this is set as default since it is common in Switzerland to consider this directly. Here we have different settings for the buckling check. So maybe here we can say, yes, I want to check the sheathing. So without this check, when we deactivate this checkbox, we will not check the second and the third line. And when we deactivate this one, we will don't check only row or line 3. And here we have different settings. So this one is the more advanced design approach from the German annex. But you can also check it according to the simplification from Eurocode, from Global Eurocode 5. I guess it's the distance in between the studs divided by 100. That's the minimum thickness for the sheathing, I guess, so something like that. Okay, but we leave this as default for now. Okay, and what we need to do is, of course, we need to assign some buckling lengths for the beams. So this is clear so far. I will define here an effective buckling length. We want to check buckling only about the y-axis. So buckling about the z-axis should not be controlling. I'll deactivate lateral torsional buckling and buckling about the z-axis. Okay, that's it so far. Okay, and when we go, or maybe one further thing, as I mentioned, when we check the normal forces inside the beam, internal force, normal force, you will see there is this compression force, and here this compression force, a tension force. This tension force needs to be covered, of course, by the hold downs, and this compression force needs to be covered by the bottom plate via compression perpendicular to the grain. So, and this we can do here. So we can go here to design supports and deflection. Okay, so here we see this is the stud ends here at node 26. And here we create a new design support. Support length should be, wait a minute, it's rotated. We use this one here in Y direction, 60 millimeter in minus Y direction. And here I use this KC90 factor, in this case for 1.25. Okay, in some annexes, or is it in Global Eurocode, I'm not sure, there is also this increasing of KC90 or about the strength by 20% because of the sheathing. But since our sheathing is also covering some forces, we will not apply this 20% increasement of the strength. Okay, so that's it. And now I have defined this design support. Okay, we can think about to apply everywhere this design supports automatically, but for now it's not planned. I can imagine that will cause some performance issue, especially on bigger files, on bigger structures with multiple beam panel surfaces, and or maybe we can apply it on the edge of a beam panel as default, and you need to add at least intermediate ones which can get some compression, but for now this is a user-defined setting. Okay, and what we do now is we design the objects. So what we want to design is here, we have another row now. It's surfaces, beam panels. As you can see, this one is activated, but there is nothing inside because everything, the beam and the sheathing, is covered here inside these beam panels. So I can deactivate this as well. And this one can be controlled here in the global setting. In the global setting, you can say, okay, for the surfaces beam panels, I want to check beams, sheathings, and connectors. But you can deactivate a single element if you like. Good, then let's run the analysis. Okay, and these are the result for now. So we see some green and red color. This is our classical interpretation. Green means the ratio is fulfilled, and red means, okay, here we have some issue. Okay, the ratio is exceeded by 10%. So let's go inside this detailed check. So here we have a new table, design ratio on beam panels. And here, for example, we can see, oh, sorry, I did a mistake. I forgot something very important. Yeah, I need to go back to edit member. And here I have to find this design support. And this design support can now deal with forces other than the shear force from the member where we have assigned this design support. And that's why we have this next tab, compression perpendicular to the grain. And here we can decide, okay, on which internal force we want to consider. Here we see this node 26 has two members connected, 2 and 4. So member 2 is the horizontal one, the bottom plate, and member 4 is the vertical one. So now we have to decide which internal force we want to use. So in this case, I use as force the compression force perpendicular to the grain from the start. So that's why I overtake the normal force. Of course, I can activate also VC, but this VC force is not giving any factor perpendicular to the grain, so load factor perpendicular to the grain. So that's why it doesn't matter if I have it activated or deactivated. But let's do it like that. Okay, and now let's run it again. Okay, beam panels, beams, and now we see here this design check. So when we open this design check, we will see exactly what is done. So we use this 13.42 kilonewton per meter from this edge start. Here we have our length, so our effective length. We add 30 millimeters on top, we calculate the effective area. And here we have our KC90 factor, and we checking if the normal force can be covered by the end grain. If not, we need to think about to use maybe some LVL bottom plate, or maybe we can support the edge start directly on the foundation. So it means to remove to cut the bottom plate on the start edge. That was also possible, and for this situation it's good. All right, the next thing is the sheathing. So when we check the sheathing, of course we need to have the same stresses inside the sheathing what we have on lines. So when we check here our forces, so internal forces and XY, we will see here this maximum value. Wait a minute, it's values on surfaces, extreme values on FE mesh. So we have here a force of 5.31 kilonewton. And when I also check here this releases and check here the actual distribution with all values, and if I would check the smoothing, without extrapolation, I would get exactly the same value here. Okay, So the question now is, should we design the surface via FEA? Yeah. So this is what we do here, sheathings. So this is actually the ratio. The ratio of the sheathing now is only 25%. Or should we check the sheathing via this equation? Of course, if you have only in-plane shear, it doesn't matter. The result should be the same. But of course, think about singularities. When you have some window openings, of course, this sheathing for the FEA result will have some singularities and therefore higher stresses. Instead of while using the second line here, then we don't have the singularities. Yeah, but of course, if you have bending out of plate as well, then we cannot completely design this surface with this design check. Okay, but let's go to this design check for now. So let's have a look. Okay, so when we check here on the right side, we see what is calculated. We get our bending moment. We get our embedment strengths of gypsum and timber. And then we see here our failure modes or our failure mechanism, based on the Johansen equations from which comes directly from the Eurocode. And as the result, we see here, it's the minimum one comes from failure mode F. So you can check the images in the standard where you can check directly which failure mode it is. And then you get here, 395 Newton. So we have here different materials. Therefore, we need to use mean value of the K mod. And this is what we do. And afterwards, we divide by the fastener distance to get also an allowable force capacity in kilonewton per meter. And then we check this shear flow, in this case 5.355 kilonewton per meter against the 7.935 meter. And sorry, I am in the wrong X location. There seems to be something wrong. Maybe I've switched it. Let's check again. Oh, okay. So there is something wrong here because the shear. No, sorry. No, all is good. Of course, we check not only eta 1. So eta 1 is about the connection, about the connector. Connector is fine with a ratio of 68%. And eta 2, this is our ratio for the sheathing. And as you can see, also for the buckling, the ratio is exceeded. And why is the ratio exceeded? We check again this factor KDA, which is actually the same like KV2, and we will rename this also to KV2. And this factor is considering some additional stresses which are not considered in this hand calculation. So we assume there is no eccentricity from sheathing to the beams, and there is no force perpendicular to the studs. And therefore, we need to consider these additional forces by using this factor 0.33. This is really low, this factor. There are some research in Switzerland about this factor, and they found out the value nowadays is higher. For OSB 3, for example, the factor here would be 0.85. But for gypsum, I have no further information. But there will be a possibility now or in the near future, to define this KV factor here manually under sheathing design check. So that's why this factor is, design check now is exceeded. But it's not exceeded because of fasteners, it's about buckling. So, but it would be nice to check what our FEA approach gives us as a result. That's why I will activate here the add-on structure stability. Okay. And with this add-on, I will calculate the eigenshape and the critical load for this load situation. Okay, so let's run the analysis. And as a result, I get the eigenshapes and I will get the critical load factor. Okay, so here let's switch to stability analysis and activate the mode shape. And the first mode shape, of course, it's the mode shape out of plane, because we do not consider for now this stiffness perpendicular to the grain, since we have activated this option. But don't care about. Let's check the second mode. And as you can see now, the second eigenshape is exactly the first shear buckling failure mode. And yeah, when we check the critical load, so the critical load is nearly at 19. So that means we would need to multiply our load by 19, yeah, to get this failure mode. And so we see it's far away from the 1, so I do not expect any buckling error or buckling issue here. Of course, we can use this buckling shape and define an imperfection of it, yeah, and do also an unsheathing design with imperfections and p delta analysis, so second order analysis. But for now, this is okay to me. But what we can also do is let's now deactivate this option. Consider connect the stiffness in the longitudinal direction, because we have, of course, stiffness also perpendicular one, because the fastener don't know that it should work only in X direction in reality. Of course, it will also act in perpendicular direction. So what we will do now, we run the analysis again. We had a shear flow of 5.1, 5.2 kilonewton per meter in longitudinal direction. And now, as you can see, the shear flow, maybe I go here by global extremes. Yeah, we have less. We have only 4 kilonewton per meter. But, maybe I can switch off the surface result. But now we don't have only the shear flow along the grain, but also perpendicular, which is VC. And here you see now we get forces. Yeah, and these forces, yeah, needs to be considered now as well. So what we do now in the design is we create a resultant of N and VC. Of course, you can think about if I should really use this high peak here, or maybe I should use smoothing option. That's why we have this setting here in the ULS config to say, for example, for 90-degree direction, I want to use a linear approach. This is what I can do. So with a linear one, you will see directly we come down from 4.3 to 2.5. Okay, but this is of course up to the user. All right, and yeah, let's see what's happening now. Yeah, we run the analysis. Okay, and let's go to connectors. And now we see at the beginning there is a warning message. Let's check this warning message. This warning message tells us something about minimum distances. And as you can imagine, the minimum distance with a 6 centimeter stud and a 1.8 diameter of connector, we would need to have at least 8 centimeter stud. But this approach here is based on the staple center. Yeah, we could use smaller edge distances by using the leg of the staple, yeah, as a nail. Of course, in this case, we need to know the width of the back of the staple, and we would need the angle. Yeah, what about the angle of staple to the stud? And this information for now we don't have and we don't consider, but I guess it's clear how you can calculate it, and it's clear for everyone. Normally we know for a 1.8 millimeter staple, which minimum start width we need. And that's why we have this option here to deactivate this check. Otherwise you would document this warning message also in the print report, and that's why we have this option. In the future, of course, we will be also able to make a more detailed edge distance check, like for nails. Okay, then let's click OK and run the analysis again, and then we should get rid of this warning message. And then we see, okay, our design check now is fulfilled. But is it only happening because of the stiffness perpendicular to the direction? I mean, it should not have such a big influence for buckling. So that's why we will check it later. Wait, first here we see the resultant shear flow now. So let's go here in this option. Oops. We can also check the forces. So we see the shear flow at this location. We see the shear flow in perpendicular direction, and we also see the, like this, and we see the resultant shear flow. Okay, so, and on the very bottom now, we see that this KV2 or KDA factor is considered with 1.0 because the standard says we need to use these reduction factors in terms of eccentricities. We don't consider it in our hand calculation, and in terms of stresses perpendicular to the grain. And therefore we fulfill this now in our FAA analysis. Therefore we decided to automatically apply here a factor of 1, which gives us a better ratio compared to the old one, and it's actually comparable with our eigenvalue analysis. So because we do not expect any buckling shape here. So this is actually the way how we do it at the moment. But since we implement this user-defined KV2 factors in the ULS config, we will remove this automatism again, so the user can control it. As default, we use the standard from the code, from the standard, and if you want to change it, then you will be able in the ULS config soon. Okay. That's it for now for this example, and then let's go to the next example. I see the time is already over, but we will continue. So I will need another 15 till 20 minutes. I'm sorry for that, but to me it was important to show you as much as possible in detail, since we will forward this webinar also to new prospects and also to our customers. So I found no way to make this shorter, this introduction into this beam panel design. Okay, so next step is of course when we do this FEA approach, then of course we can deal with openings, and the question now is how we can implement or how we can create these openings. Of course, the easiest way would be to use this RFEM opening. In this case, new rectangular opening. So let's define some openings here, and we will see. Looks good so far. We can hit the calculate or show results button, and that's it. But unfortunately, it's not as easy as it seems, but it is easy. But we need to do something additional. So for example, when I check here now the beam panel mode, we will see that this studs runs through the window, which is of course not wished, and we have no sill, rib, and no heater. to do so, we need a nice feature which is called surface cells. And we need to activate the surface cells here, and then we can click OK. Okay, we don't see anything, so it's still the same as before. But now we can create cells, and now we can use these cells to create the opening. What we can do is we can add some lines here and give exactly the orientation of this opening. This can be done manually, with lines, or simple right-click the surface and say here, create surface cells due to the opening in Y direction. So we see here the Y direction goes downwards. So we want to create these lines in Y direction. And when we do so, we see these blue cells. And when we now check the beam panel mode, we see, the opening was successfully created. So we have a stud next to the opening, and we remain with our stud spacing 60.25 from here to here, from here to here, from here to here, from here to here, and so on. When we click on the surface, on the sheeting, we see perfectly that this sheeting now is divided also on this opening. And this is actually a way how we introduce the openings. In the future, there will be some user-defined setting of the studs and openings, so we will be able to make more, or we can handle more situations. For example, we can continue with this member until this stud, for example. That's also an option. But for now, this is how we deal with the openings. We have these surface cells. Okay, but when we deal with that, now we want to do it in a better way. We don't want to use this linear support, but we want to use a nodal support to model our anchors, our hold downs. So I create a visibility of these elements. Okay, and I will define my support. So in this case, I want to model this hold down here and also here. Of course, when the wind comes from the opposite direction, we need it on both sides. So I create a simple support here. This support can handle both. It can handle compression and it can handle tension for the hold downs. Dependence, if you get positive or negative force, we know which, for tension, of course, we need to place some hold downs. Then the intermediate supports, I create a new one as well, but these support will be will fail if negative contact force. So in case we get uplifting force, here we go. In case we get some uplifting force, this design or this support should not work. So I placed now a support under each stud to cover the compression. Okay, so and what we can do now is we need to redefine the load, since due to the opening, the member numbers get changed. So we have to look if we can optimize this situation as well. But let's check the member loads. And it's assigned to no member. It should be applied on these members here. And let's go with uniform. It doesn't matter. 5 kilonewton per meter. Okay, that's it so far. We remember we had a deformation of 4.1 millimeter. Due to the opening, I expect, of course, a bit higher deformation, and also because of the supports here, which will fail under tension, I expect a bit higher deformation. Okay, let's run the analysis. Okay, I could deactivate this stability check. Okay, but what we see here, of course, we get perfectly again the shear flow and also considered around the opening by this FE approach. And then we follow the same design rules like I showed you on this simple example without openings. So nothing special, but let's check the deformation. Okay, so we see good. We have higher deformation, 6.7 millimeters. Let's check the forces. Okay, let's focus on the vertical forces in C direction only. Okay, we see here in the very beginning, we will get some compression here, but as you can see here, we will have failing support, so we will not cover any tension here, which works quite nice. And we would need to apply a hold down which covers the 15.2 kilonewton nodal force. And here we have the compression force. Good. We see that also this walls, the small walls, will also be able to wait a minute, we can deactivate this one. Will also be able to take part of the deformation. So when we think about the classical approach, what we do in Eurocode, what we need to do is we can nearly neglect this area. So in total, we would consider only this area here, because the opening cannot be considered, and this one are so small. We would need to check the deformation by hand. We would place some hold downs here, which definitely will cause some extremely high tension forces. Not a really good idea. Of course, there are analytical approaches. For example, this force transfer around opening method, which deals with openings. We did some comparisons, and the comparisons were really good. Of course, we are a bit more economic about than these analytical equations, but let's compare it with a classical Eurocode approach. So I will copy this node and this node by -5 meter, and I will create this beam panel again. Here we go. Okay, so it's a bit, wait a minute. It doesn't matter. We can also rotate. Where is it? Specific axis. Let's rotate it by 90 degrees to have nearly the same orientation like here. So it's nearly the same. It's not important. And then let's support this. Shear wall in the same way. So we could also use this one. And here we go. And at the end, of course, we have here applied 25 kilonewton per meter, 25 kilonewton, 5 times 5 kilonewton equals 25. So I will add a new member load here in X direction, uniform total, 25 kilonewton. Okay, perfect. It creates an 12.5 kilonewton per meter unit load. And now let's check and compare how the openings, or how the considering of the openings and its stiffness around the openings will help us. Okay, I will run the analysis again. And then of course, I need some support at the top edge on the heater. Here we go. Okay, to simulate some diaphragm. And then let's compare the results. Okay, so in the beginning, we can directly see we apply the same load. So we have 50 kilonewton, 25 here, 25 here. On this approach, yeah, you can see the hold downs, yeah, need to be covered by 15.2 kilonewton per meter, 15.2 kilonewton, which is absolutely possible to cover with also simple hold downs. But compared to these hold downs forces with 36 kilonewton, yeah, this can get quite challenging. And also the deformation. So let's check the deformation in beam panel mode. Yeah, it's 11.2 millimeters. So we get nearly, yeah, doubled deformation. So, and of course, this is the big advantage, yeah, of this FEA approach while modeling timber shear walls. Yeah. And this was just now a basic, yeah, introduction into this topic. I plan to do some further webinars in the near future about about the bracing systems and for timber shear walls. And there we will see more advantages and, yeah, more economic design. Okay, so that's it from my side so far in RFEM. Let's go to, or yeah, maybe we can. Yeah, come, we can. Let's design also the bottom surface, because of course we need to check if the design check is fulfilled. That's clear. Otherwise, we cannot compare the results. Okay, and we see here, yeah, that the simplified method or the simplified wall here is exceeded nearly by 100%. So we get a ratio of 200%. And here on the bottom, we see, yeah, the design check is nearly fulfilled, which is, yeah, quite nice. Perfect. Of course, we need to check our deformation. We have wall height of 3 meters. Yeah, let's assume L over 300 for the deformation. We are still fine in this case with 6.7 millimeter. Okay, but now let's go to my last slide. It's about the outlook, what we have planned for the future. So the next step will be we will release the design of the beam panel according to the US standard. This is this SPIDWIS document. This will be available hopefully in a few weeks. Yeah, I think so. Then another topic is varying connector spacing within a surface. So at the moment we can define only one connector spacing within a surface, but of course the intermediate studs normally or typically can will not get so much load. Of course we can use smaller distances of the spacing. Then we think about wall-to-wall and wall-to-floor connections like here, because at the moment if you apply the center lines here for the surface, yeah, it can cause some conflict because the sheeting in beam panel mode is overlapping with the other elements, yeah, and this needs to be done or solved somehow. Yeah, at the moment it's not a big problem because we can easily use some rigid links to connect the walls from center to center. That's also possible at the moment. Okay, as I mentioned already, it is the custom stud arrangement. So yeah, could be helpful, I guess, to create some user-defined pattern. Then we will get some graphical result representation of the beam panel. That means when we are not in beam panel mode here, you see you get no results. Yeah, and we will display here also result for timber design on the whole surface. So we will show one ratio with the maximum ratio of the single elements, and it helps you when you have more beam panel surfaces to determine which one is governing. Okay, then yeah, of course, gable shear walls. So it's also a big issue. Okay, maybe the forces will not so high inside because the triangle, yeah, works as it should work, and the forces are maybe not so much transferred via the sheathing, but via our triangles. And yeah, at least, yeah, at the end, It's about the definition and design of the shear anchors, shear connectors, and the hold downs, which will be available hopefully soon in our add-on components. Yeah, but this will take a while, but this will we will release this add-on to the beta status soon, so hopefully we can deal with the hold downs in near future without checking any tables about the load capacities. And as I mentioned already, there will be some additional webinars about timber frame constructions in the near future. Okay, so I came to the end, and I want to say thank you to you all, and I will hand over to Andreas. Goodbye.
Thank you, Gerhard, for a nice presentation. At the end of the webinar, I have an additional hint to our online courses. For example, there is the RFEM 6 Masterclass course. It's a course for beginners. Then the Eurocode 2 course for the concrete design with RFEM 6. The Eurocode 3 course for the steel design with RFEM 6. The Eurocode 5 course for the timber design, and the Eurocode 8 course for the earthquake design. If you want to get more information and prices, just scan the QR codes here or click at the links. You can get such an online course for free if you submit a customer project. Just scan the QR code or click at the link. The other way is to send me an email to info@dlubal.com, and I will answer you. I write you what I want to have for data from you. It's not much work for you, I promise. So then our free online services, for example, the Dlubal community, you can ask questions there, and we or other users will answer you. Then the GeoZone tool for the determination of snow, wind, and earthquake loads. The cross-section properties, you can download 3D models as template for your project, for example. If you don't have our programs, then just download the 90-day full trial version. And you can explore all our free services when you scan the QR code or click at the link. More information can you find on our website, dlubal.com. For example, knowledge base articles. You can ask questions to our AI assistant, Mia, all the time, 24/7, and she will answer you. Okay, that should be also all from my side. I thank you for your attention. Thanks to Gerhard for the presentation. I wish you all a nice rest of the day. Maybe we meet each other in a future webinar. See you. Bye-bye.